Welcome back to our channel. Today we are going to discuss a new topic called dining dining philosopher problem. This is one of the synchronization problem. As I know here, how we can resolve the what is the exactly the meaning of dining philosopher problem and how we can resolve the help of semaphore like that. So already told you it's a problem where always helpful to illustrate the resource allocation challenge in the concurrent system. Moreover, it involves the philosophers where always have the alternative thinking between the uh, things like eating and they also need two forks here. If you have two forks, they can eat. Otherwise, not possible. And moreover, this kind of situation may create a deadlock. How we can avoid with the help of semaphore and shared data here. Here, let's assume that there will be a dining class of problem, have a P1, P0, P2, P3, P4, and having the fork like F1, F0, F2, F3, F4, and so on. Here, if philosopher want take the food, he can use two pair of spoon. Suppose if you take one spoon and unable to take the one fork, there is a problem. Then food is I can eat. So here, you have to give equal chance for everyone. That is the one concept here. So five philosophers sitting around here and they have only five chopsticks there. If they want to eat at a time, not possible. One by one they can eat and they can take food also. So here you can develop an algorithm where there is no plus of staff. That means every philosopher have the chance to eat. That means the chopsticks initially to zero, initially assign the zero, and such a philosopher having the semaphore concept that is weight chopstick by and weight chopstick of I plus 1 by percentage by here and eat. So if at all initially it will wait and go for eat and after eat it gives the chance to another one. That's the meaning here. So second of chopstick of I plus 1 by 5 followed by the coding here. So here the philosopher can think if they feel hungry, it will decide to eat. Otherwise they can think only. And then let's have the program here. Chai, sorry, chopstick of 5, instant 1. Let's assume that we are going to give the chance for P0. So class of P0 will eat. We can the continue code like do weight of chopstick of 1, F0 and 0. You can write the code F0. That means you can take the one fork and have a chance to get the another fork here. And once you complete the eating process, you can release the lock here. That is possible here. Then there will be a chance of starvation here and same thing I'm telling you. For a P1, P0 taking and P1 taking, there will be a starvation or there will be declare happen. P0, P4 also taking, there will be a problem happen here. So once you give the solution, either first of all, the philosopher will take the food P0 and give the chance of P2 and give the chance of P3 and so on. And how do you get the solution? The better solution for dining philosophy is share data. So say we can write the code like the state of 5. There will be a thinking method like thinking, hungry, and eating states. And self-apply we are declaring and semaphore insert to all zero here. And meters are following a variable that is semaphore of insert to 1 and left of I plus 4 by 5 percentage, a left neighbor and followed by right I plus 1 of percentage by right neighbor. So here we are going to apply the two conditions that is void test and put down here. Then we will understand here. So we are writing the code class of I, set of I is equal to hungry, then weight of meters here, test of I. That means here what we want to convey here, the void test of delta I. If at all, let's assume that P0 feeling hungry. If at all state left of eating and state of I is equal to hungry and state of right is not eating. That means what? Only state, the meaning is only philosophy 0 is not to eat. So that reason, the remaining person not feeling hungry, they will allow. That means P1, P2, P3 won't take the food here. Sorry, won't take the food and take the fork chopstick also. That's the meaning here. So they are not feeling hungry. That's the meaning. And then one more condition: if state of I is not eating, weight of self of I after updating, it become weight of meters and put down of I. That means once the P0 completed, you can put down the fork and give the chance for P1, P2 or anything. That's what finally can be here. So there is no deadlock here. What you understand here, and we can write the code again. If at all left state of left not eating, state of I hungry, and state of right is not eating. That means left and right side as in the diagram not eating, and here in the diagram. So P0 will get the chance to eat completely, no disturbance, and then give a chance to P4, P5, and so on. So this is about dining philosopher solution. That means how we can find with help of here. Thank you for watching. Thank you for watching video. Thank you.